So I think it's about time to start. Yorgo? Okay. So good morning, everyone. I'm Dimitris. I've been working with Angular for the past 10 years. It's just a short time. And today I want to show you how the NgRx Signal Store gives us superpowers when it comes to managing state in Angular applications. State management is the process of handling application state over time. But to make it simpler, let's think of our application like a library. If our application is a library, the state of our application is about the books and their position any given time. If we only have a couple of books, and we are the only ones reading them, we know where every book is, and we can be happy without state management. If our library has more books, and maybe there's a friend or two that come visit us and borrow our books, we might need a notepad or some simple management to make sure that we know where every book is. But if our library turns bigger, and suddenly there are many friends who want to come visit us and borrow our books, then it might get complicated to keep track of the changes in our library just with a simple notepad. And that's why we need good state management. As our library, as our application grows, and more developers or users come into play, good state management enables us to continue building features with confidence, knowing exactly where data lives, how it changes, and who reacts to it. So today we're going to talk about state management, not Pokemon, sadly. But I promise you that state management is going to be just as exciting. First, we will explore signals, Angular's reactive primitives. We'll see how they work for managing component state and when they sign. Then we will extract that logic into a signal store using methods. This will give us better separation and reusability. Finally, we will introduce events to fully decouple our architecture, unlocking advanced patterns and making our state management reusable. Finally, we will compare all approaches and discuss which approach to use based on specific criteria. Let's start with signals. Signals are Angular's reactive primitives. They were introduced in version 16. They are like smart containers that know when their value changes and automatically notify anyone who cares. Signals can contain any value from primitives like a number to complex data structures. In signals, we have three core building blocks. We have signal, which creates a writable reactive value. It's like a variable that broadcasts changes. Computed enables us to derive new values from existing signals, and it automatically recalculates when dependencies change. In this case, the dependencies of the computed is the count signal. And the third building core primitive is effect, which enables us to run side effects when the value of any included signal is modified. In this simple example, we have a count signal. We initialize it to 0. We have a computed that doubles it. And right below, we have the effect that will console log the value of the double computed whenever the doubled value changes. In the end, we set the value of the count signal to 5. So anyone can tell us what is going to be console logged? Please?
10, because the computed signal will double it and then log the result.
And that's correct, thank you, exactly. So the effect will execute whenever the signal value changes, the signal value of the included signals. Let's move on to another example. In this example, we have a signal holding our tasks array and 3 computed values deriving values from it. Task count computes the length of the tasks array. I don't know, is it clear enough for everyone? Zoom in, yes, right. I'm not sure how I can zoom in here. I can zoom in. Now it gets complicated. Maybe if I zoom in Here. Is it better? Okay. Right, so again, task count computes the length of the tasks array. Completed count filters and counts completed tasks. And progress percentage calculates the completion rate of tasks. Each one of these values is a computed signal that automatically recalculates when the tasks array changes. And in the template, which is, if I zoom out, right. Yeah, it's really difficult to zoom in with this setup. Anyway, in the template, we invoke these signals like functions. Angular tracks the dependencies of the computed values and updates the DOM only when these specific values change, and there is no need for async pipes or subscriptions. In this component, the code is declarative. We describe what we want and not how to manage it. It is self-contained. Everything this component needs is right here. And it is performant. Angular will only re-render the DOM when these specific computed values change or their dependencies. But what happens when a component needs to do more? Yeah, let's now take a task list component. This component needs to do real work now. We need to load tasks from an API, create, update, delete them. We also need to handle loading states and errors. This is where things get interesting. Look at the load tasks method. Now it's managing loading state, it's making an API call, it's handling errors and updating the task signal. That's 4 different concerns in one method. And we would need to repeat this pattern for update task, delete task, and create task. What if we need the same logic in a modal dialog or a different page? We would have to copy-paste the code, and now we have duplication. What if completing a task needs to trigger notification or update user statistics? Suddenly, we would have to inject multiple services, and we would couple our component to the app architecture. And how do we test this? We need to instantiate the component, mock the API service, trigger the method, and assert the signal values. This will turn into an integration test. This will not be a unit test. The signals still work fine for now, but we've outgrown component local state management. We need to extract this logic and separate our concerns. And Signal Store is our answer to the extraction problem. It's a lightweight feature-level state container that keeps all of our state management logic in one place, separate from the user interface. Think of it as a specialized service that uses signals under the hood. And in a Signal Store, we can define our state, our computed values, and our methods for managing the state, all in a single unit that is reusable across our code base. Most of the methods that we will see in the following examples come from the NgRx Signals package that can be installed through your favorite dependency manager. Now look at the architecture transformation. Before, everything lived in the component, UI, state, logic, API calls, and for every component, we would need to duplicate this. But once we extract the business logic into a Signal Store, the component becomes a theme presentation layer. It renders the user interface and dispatches actions. This gives us real separation of concerns, makes our state management testable in isolation because we don't need any components to test it, and it's reusable. We can inject it anywhere in any component we want, so it can be used by multiple components. Let's see how we build one. So here are the task methods from the component we saw before, extracted as a Signal Store. A Signal Store is built through composition. We can chain together features to create our store, each one adding a specific capability. First, withState defines our state shape. Here we have the tasks array, a loading flag, and error state. This is our single source of truth for the task state. Next, withComputed enables us to add derived values, just like we did on component level computed signals, but now they live in the store. For instance, completed tasks filters the tasks. Task count gives us the length of the tasks, and this automatically recalculates when the underlying state changes, which in this case, the underlying state is the tasks array that we defined with withState. And with methods enables us to add our business logic. Notice that we inject the API service here because the store can have its own dependencies. The load task method uses pagination to update the store immutably. Initially, it sets loading to true, then it fetches data from the API, and finally, it updates both the tasks array and the loading state. And there are more features that we can use to compose our store. Here we have withEntities and withHooks. If we're managing collections, tasks, users, products, withEntities can prove really helpful because it adds normalized entity management out of the box. We get an entity signal with our array, an entity map for fast lookups by ID, and helper methods like add entity or update entity that handle updates on our entities. And we will see them in action in the next slide. And withHooks gives us lifecycle methods. On init runs when the store is first injected. This is perfect for initializing data. We also have on destroy, which runs on cleanup. This is useful for canceling subscriptions, if we have any, or saving state. For example, here we auto-load tasks. When the store initializes, any component that injects this store will trigger this method on the store's first injection. It's all composition. We mix and match what we need. Another small store might skip the entities, and another might need more hooks. We should only compose what fits our feature. Now let's see how we can use computed values to create powerful derived state. withComputed enables us to build complex derived state that automatically stays in sync. Look at the progression here. Task count is trivial. It's just the length of the store entities. But filter tasks combines two signals, the entities and the filter status. If we change either one, it will recalculate. Selected tasks is a great pattern. We store just the ID of the selected task in the state, but expose the full entity through a computed value. This avoids normalization and keeps our state minimal. And completion rate shows how we can build on other computed values. It uses task count internally, which is also a computed value from the store. And Angular tracks all the dependencies and the dependencies of dependencies in order to update only the affected values automatically. And it is efficient because computed values are lazy. They will only calculate when something reads them. If a computed isn't used at all, it will not be executed. And this is what we've been building towards. Look how clean our front-end components now. It's now pure presentation. It only injects the store, and the template reads signals directly. Task count, completion rate, the filter tasks, these are just computed values from the store. The component doesn't care how these work. All of these values will be calculated and presented automatically. And when users interact, clicking filters, completing tasks, or deleting tasks, only store methods will be used. We have set filter, complete task, and delete task. These are store methods. The component doesn't care how these work, if they involve API calls or anything. The component only dispatches user intention. There is no need for subscriptions, async pipes, or manual change detection. Everything is synchronous signal access, and Angular keeps tracking dependencies and updates the DOM accordingly when there are affected updates. And when it comes to testing, we can test the store logic in isolation with unit tests, and we can test the component with a mock store, also with unit tests. We now have true separation of concerns. This pattern feels good now. The component is small, the store we build is efficient, reusable, and testable. But what happens when features need to coordinate? And here's where method-based stores hit their limit. Let's say completing a task isn't just about updating the task. It needs to trigger a cascade of updates. For example, when a user completes a task, we want to award them points, show a success notification, track the event on Google Analytics, maybe invalidate something in another store. This is normal application complexity. The easiest thing is to inject all these dependencies into our task store, call the user store to add points, call the notification store to show a notification, call the analytics service to track the event. But now our task store is coupled to everything. Testing requires merging 4 different services. If we change the notification system, we would need to adjust the task store as well. And if the user store or another store also needs to update tasks, for example, when the user upgrades to a business account, then we will get circular dependencies. And we lose the isolation we worked so hard to achieve. So we managed to separate user interface and state, but we have created tight coupling between stores. Now we need a way for features to coordinate without knowing about each other. And this is where events come into play. Event-driven architecture is a different way of thinking about our application flow. Instead of components and stores calling each other directly, they communicate through events. In the method-based approach that we had before, the method complete task directly called other stores. It has to know about user store, notification store, so it's becoming coupled to their APIs. In the event-driven approach, complete task will only dispatch an event saying a task was completed, and that's it. Task store responsibility ends there. Now, somewhere else in our application, completely independently, another store can listen for task completed events and act accordingly. For example, notification store can listen and show a success message. An analytics store can listen and track the event on Google Analytics. Each feature can react on its own terms, and the task store doesn't care. Events are named in past tense, task completed, not complete tasks, because they describe what already has happened. And now we're going to take our existing task store, the one with those dependencies that we injected, and refactor it to use events. When we're implementing an event-driven architecture, most of the times we follow 4 steps. First, we define events, type-state definitions for anything that can happen in our application. Second, we implement reducers, functions that update our state when events occur. Then we implement effects. Effects are async operations like API calls, which on their end can dispatch result events. And finally, we dispatch events from our UI components and make them completely decoupled from business logic. Let's start with defining our events. We will use event group. This comes from the NgRx Signal Events plugin. We will separate our events into 2 distinct groups. We have task page events for user intentions and task API events for system outcomes. The task page events represent what the user is trying to do. When a user opens the application, creates a task, or completes a task. Task API events represent what actually happened in the system. Every async operation gets a success and a failure event. For example, when we load tasks, we need the task loaded success event and the task loaded failure event. For most events, the payload is straightforward, but you will notice that in the task status change page event and in the task status change failure API event, we are passing the previous state in the payload in order to enable optimistic updates of the user interface with rollback. We will see this in action a little bit later. And now let's see how reducers consume these events. Reducers are the heart of event-driven state management. They are functions that listen for events and return state updates. We wrap reducers in a Signal Store feature. I know that this is small right now, but don't worry, all of the examples and the code will be shared in the end of the slides. So again, we wrap the reducers in a Signal Store feature. This makes them composable and reusable. Inside, we have withReducer, which contains multiple on handlers, each one listening for a specific event. Notice the pattern. Each on handler receives an event object. The actual date of the event is in the event payload, So for instance, when task status changed fires, we get the ID and the status from the event payload. Every state change has to go through a reducer, and this is why we can trace every mutation back to an event. Again, reducers handle all the state updates, but then you would wonder who handles the APIs, who dispatches those success and failure events, and that's where effects come into play. Effects are where async operations happen. They listen for events, call services, and dispatch result events on their end. This bridges user intentions with system outcomes. First, notice the usages of RxJS observables. The task service API returns observables. Therefore, we can chain RxJS operators. This gives us cancellation and composition capabilities. And the part of the composition is exhaust map, which is an RxJS operator that will ignore new events while a request is pending. In this case, when a user tries to update a task multiple times, maybe he's a little bit impatient and he clicks the mouse way too fast, all attempts after the first one will be ignored until the first effect execution completes. On success, we use concat map to dispatch the success event with the ID and the new status. And this will confirm the optimistic update. We will see this in action a little bit later. In case of an API error, catch error will dispatch the failure event with the ID, the previous state, and the error message. So now we have events, reducers, and effects. The final piece is to dispatch events from our component. And this is where it all comes together. Our component will inject the store for reading state and dispatching actions. In NgOnInit, we dispatch the opened event. The component doesn't do anything else. It just describes what happened. The user opened the page. Let's take a look at on status change. When the user clicks to complete a task, we dispatch the task status change event, and the component doesn't know about the optimistic update that will happen in the reducer, the API call happening in the effect, the potential rollback if the API call fails, or if other stores are listening to this event. The component just broadcasts. The user has changed a task status. This is a bigger picture. I know it's probably hard to distinguish the methods, but again, all of these examples will be shared. So when the user moves a task on the user interface, we will see a live demo, I think in the next slide. The component will dispatch the page event. The reducer updates the entities optimistically. The update of the entities causes a template re-render. In the meantime, the effect will call the service, the API service, and depending on the result, the appropriate API event will be dispatched. Let's say that in this case we have a failure, so we go to the catch error, and the reducer will have to revert the optimistic change. It updates the entities, so again we will need to have a template re-render. As you can see, the component only participates while dispatching the events and rendering the template. And let's now see this in action. I will also try to zoom a little bit better. Right, so we have a task tracker here. The console, I suppose, is not visible to anyone. Let's see how I can make this bigger. Yeah, I guess that this is a little bit better. Right. Yeah, as you can see, we have already completed some household tasks, but let's say that now it's time to clean the kitchen. Clean the kitchen has moved to in progress. And we now see all the sequence of events. First, we dispatch the event, the page event from the component. Then the reducer does the optimistic change on the template, on the state, I'm sorry. Then, in the meantime, the effect is listening and is triggering the API call. The API call was successful, and the effect confirms that the task status was successful. Yes. But now let's try to pay the bills, and I have a suspicion that our API doesn't like paying the bills. Let's clean the console and let's try to complete this. Exactly. First, in the UI, you see that, let's do this one more time. The task will optimistically move to the done column, but then it returns back because the API call fails. And again, we have the full sequence of events. We dispatch the page event from the front end. The reducer does the optimistic update on the state. The effect calls the API, and the API calls fails, which causes the optimistic update rollback. This is what we saw on the user interface. And this is how the event-driven architecture actually works. Are there any questions on the live demo, maybe? We can also open for questions later, okay. Once we have established event-driven architecture, we can also do our testing in separate layers. In the reducer, we pass in a state and an event, and we get back a new state. There is no need for mocking services or setting up complex test beds. Effects coordinate async operations and event dispatching. To test them, we mock our service layer, control what it returns, and verify that the effect dispatches the correct result events. Store tests validate the complete flow. These tests should give us confidence that all of the pieces work together correctly. Finally, in the component, we can simply mock the store and verify that the correct events are being dispatched on user actions. So we have explored 3 signal-based approaches. Let's see when to use each one. Component local signals work great for small isolated features, a counter, a toggle, simple form state. You don't need extraction if the logic is trivial and specific to one component. The overhead isn't worth it. When your feature grows, multiple components need the same state, and business logic becomes complex, then it's time to extract to Signal Store with methods. This is the sweet spot for most feature stores because you get separation of concerns, reusability, and testability without the complexity of events. But when features need to coordinate, for example, when completing a task, updates points or shows notifications, go for events. Or when you need advanced patterns like optimistic updates with rollback, the decoupling and predictability are worth the additional effort. But also keep in mind that these aren't competing approaches. These are evolutionary stages. So you can start with signals, extract to a store when component logic gets too messy, and add events when store coordination becomes painful. Architecture should serve our features, not the other way around. We should use these patterns to build maintainable, scalable applications, but always keep asking ourselves, what does this feature actually need? And that's everything I wanted to show you today. Let me leave you with some resources, and then we'll open up for questions. If you want to get started with Signal Stores, the NgRx documentation is an excellent starting point. All the code from today's presentation is on this GitHub repository. Yes, the repository includes the complete task store implementation for both method-based and event-driven approaches. Then you can check my own Signal Store guides on my Dev2 profile, which is down here, and come say hi on LinkedIn if you feel like it. Thank you. Do we have any questions?
So comparing to a more traditional way of writing components, in the table that you showed, we have the in-component signals, which would be comparable, I guess, to the traditional way of doing API calls injecting service. Then for someone using NgRx currently, and not the Signal Store, just the component global stores, I guess the equivalent would be that the method store is the equivalent of component store right now, and then the event-driven store is the equivalent of the global NgRx store. Is that a fair comparison?
Yeah, it is a fair comparison when it comes to signals. Yeah, that's right.
So someone, in your opinion, if they want to follow an update path to Signal Store from an NgRx store, you would base the existing component stores to method stores, and then the global state you would handle the event data.
Exactly as you described it. First, we extract to the method-based store, and then extract logic to events, but step by step. Again, you can combine these methods. It's not like you go one way or another. Anything else? I suppose no. So thank you again, and enjoy the rest of the conference.